Hello, welcome to this presentation. This is Nooralishahi. The title of this presentation is a novel drone-enabled approach for gas leak detection using thermal image flow analysis. This presentation involves 4 sections: introduction, literature review, method, and experiments. The first section is introduction. What is gas leak? Gas leaks and emissions are a common challenge for various industries like petrochemical or oil and gas industries, resulting in financial losses and possibly human injuries. Gas leaks can cause human injuries. For example, in confined spaces like building, even a small leak in pipeline can gradually build up to be extremely lethal or even explosive amount of gas which can endanger staff. Another area is global warming. Release of some gases, such as natural gas or propane, into the atmosphere is harmful due to their effect on global warming. Also, we have fugitive emission. Fugitive emission is the emission of gases from industries' equipment due to the leak or other sources of gas release which can lead to increase in air pollution. Generally, the early detection of any hazardous gases, such as VOCs or methane, can increase the functional safety of the system and prevent any health risks for the personnel. There are many tragedies caused by gas leaks all around the world. For example, in 2019, in the United States, a market had to be temporarily closed due to the carbon dioxide gas leak. In China, 2019, 10 people died and 19 injured after carbon dioxide leak on a cargo ship. And in India, 25 people hospitalized after a chlorine gas leak from waterworks. Gas leak can cause financial loss for companies and end users. For example, rapid expansion and construction happening in different industries can increase the probability of gas leak, especially in the pipelines. For example, the report published by European Gas Pipeline Incident Data Report showed that between 1970 to 2016 in Europe, the growth rate of pipeline was 21%, which the total length of pipeline reached to 2,200,000 kilometers. This amount of expansion increased the probability of gas leak dramatically. Regarding the end users, leaks in buildings and facilities can cause end user financial loss. For example, a study conducted by Google Earth and EDF, which collaborated by equipping Google Street View mapping cars with required sensors to map the methane gas leaks in various urban areas like Boston, Indianapolis, and New York City. Google Earth and EDF actually team up to install sensors on Google Earth cars to find a cheaper and safer way for assessing leaks in urban areas. You can see here different cities and how much gas leak they could detect and the severity of those gas leaks. Why to use drones in gas leak detection? One of the fundamental requirements for an effective corrective measure is the identification and quantification of the leaks, like the level of gas concentration and approximation of source location and so on. So the proximity of equipment or inspectors to the possible leaks increase the reliability of analysis. Also, in case of dangerous gas, an inspection of these sites can put the personnel at considerable health risk. So using drone make us able to make this kind of inspection remotely. The other part is access limitation. Likely access limitation imposed by the conditions like height or temperature of an operating facility can make the inspection very challenging or even impossible. But using the drone and their flexibility of maneuver, we can fix this problem. There are other benefits of using drones for gas leak detection, like easy and free positioning, quick deployment or launch, limit to zero downtime for equipment and systems, and low insurance costs. Generally speaking, drones are very useful when the size of inspection area is very large, in case of remote and inaccessible locations, and for inspection of hard to reach or dangerous sites. Generally, we can say that drones can increase the frequency, consistency, coverage, accessibility, and safety of the inspections, and at the same time decrease the cost and time of inspection as well. The next section is literature review. Gas leak detection methods can be categorized into different groups based on different aspects. So, for example, based on detection approaches, they can be categorized into direct and indirect approaches. Direct approaches involves the use of systems and sensors like thermal camera to find the possible gas emanations. In indirect methods, the leaks are detected by measuring the variation in some of the parameters such as flow rate or pressure. Based on human involvement, gas leak detection methods can be categorized in automatic detection, which mostly includes installed sensors and monitoring system, semi-automatic detection, which requires certain human inputs or assistance, and finally manual detection, which the sensors need to be directly handled by operators. The most popular approach for classification of gas leak detection methods are technical nature, which categorize these kind of methods into two groups, hardware-based and software-based. Hardware-based methods use a sensing system to detect possible gas emanation. Software-based approach continuously monitor and analyze the parameters of a system to detect possible signs of gas leaks. At the right side of the slides, we can see different methods that can be categorized under each of these approaches. In 2020, a study used a microcontroller-based gas sensor array together with an imaging system installed on a drone for the sole purpose of localizing CH4 emission hotspot. Another study presented an aerial near-infrared laser sensor platform, creating quantitative plumb images by scanning laser beams for locating and visualizing methane gas emissions. This study demonstrates that the introduced active laser-based QGI technology is more sensitive, quantitative, and independent of ambient conditions than passive thermal infrared optical gas imaging systems. In another study conducted by BAM, Federal Institute of Material Research and Testing in collaboration with Air Robots, they presented a micro UAV platform for measuring hazardous gas concentrations and locating their sources using 5 gas detectors embedded in an aerial platform. Also, another study introduced a real-time automated technique for gas leak detection, which they use FRCNN neural network integrated with optical gas imaging technology to tackle the gas leak detection issue. Finally, one study addressed the visualization of methane gas leak detection by using a LWR multispectral infrared camera installed on a hexarotor drone. Next section is method. The algorithm introduced in this study uses optical flow analysis to enhance the visibility of gas flow and detect the gas emanation. Although optical flow is an effective approach in forming motion map of consecutive frames, it imposes some challenges when the image stream recorded by a thermal camera installed on a drone. So there are some challenges we had to address before going further. For example, the first one was the possible movements and changes in the background can disturb the result of the algorithm. So in this study, it's assumed that beside the gas flow, there is no other significant movements in the background assisting us to focus more on the detection of gas flow in the image stream. Another challenge is the sudden movement of the drone while hovering due to weather condition or pilot decision. So in this study, the use of video stabilizer techniques are investigated to see how they can improve the performance of the algorithm processing the aerial footage of gas leak. The changes in the thermal images due to the different reasons such as changing field of view can change the thermal radiation received by camera because of variation in exposure levels, angle of views, and the automatic determination of radiation range applied by advanced thermal cameras. So in this study, there are a series of pre-processing steps that we applied in order to reduce the effect of these kind of changes and variations. Here you can see an abstract view of the introduced algorithm. Instead of processing all the frames and demonstrating the results, we actually took another approach. We used window buffering in order to provide a near real-time visualization of gas leak. So we retrieve a frame, stabilize it, and then keep it in a buffer until the number of frames reached a certain amount of threshold, and then we pass the whole batch to the gas leak detection algorithm that presented in this study in order to be processed and extract the features and points that we want to extract, which is hotspots, probabilistic map of gas emanations, and area with highest flow intensity. So it will be a continuous process of the frames. It can be used on online image streams, and it processes all the frames in real time. Video stabilization is employed to remove undesired motion between consecutive frames that recorded with mobile systems like drones. Stabilization techniques align the following frames based on local features to minimize the unwanted motions. In this research, we investigate the feasibility of employing image stream stabilization to omit the existing motions in thermal or visible footages recorded by an aerial platform while hovering. There are two types of video stabilization methods: spatial domain methods and frequency domain methods. Spatial domain methods use intensity patterns or features to match images and define the proper transformation model. However, in frequency domain methods, they determine the transformation parameters while operating in transform domain. Spatial domain methods have higher accuracy. They can handle larger transformation, but they have higher computational cost. On the other hand, frequency domain methods are more resilient to noises, and they have lower computational cost compared to spatial domain methods. So in this study, we actually focus on frequency domain methods. The investigated scenario defined in this study is the drone record the suspected area while hovering with limited motion. A method that we use for video stabilization is based on phase correlation technique to remove small motions of drone while hovering. The resulted frames were cropped to provide the area visible in all the processed frames. Gas leak detection methods presented in this study has three main steps: pre-processing, flow analysis, and gas flow characterization. Here you can see process flow of the proposed algorithm. So we have intensity-based histogram and adjustment and background removal, adaptive thresholding for the pre-processing step, and then we have estimating dense optical flow, filtering the motion map based on their value, and the combination of all of these to calculate the probabilistic map of the motions based on their magnitudes in the flow analysis. And we use a histogram based segmentation to find hotspot and the areas with the highest flow intensity. So intensity-based histogram adjustment is the first step in the gas leak detection method that presented here. The algorithm transforms an image in a way that the transformed image histogram matches the histogram derived from a reference image, which is the first frame in one batch. You can see the result here, how much they got similar after the alignment. Then the next step is the removal of static pixels based on the reference frame. In this approach, the background pixel values are determined based on the local differences in the frame with the reference frame. This step will help us remove irrelevant information and filter out small motions in the scene. Then we apply adaptive thresholding. Adaptive thresholding is a form of thresholding that takes into account spatial variation in illumination, and it's very suitable for real-time processing of image streams. Finally, we go to flow analysis, and we apply an optical flow analysis algorithm. Optical flow is the motion of objects between the consecutive frames of the sequence caused by the relative motions. It can be of two types: sparse optical flow and dense optical flow. Dense optical flow computes the optical flow vector for each pixel of the frame, which may be responsible for its slow speed but leading to a better accuracy result. It can be used for detecting motions in the videos, video segmentation, and learning structure from motion, or SFM. In this study, the method we used is a frame-back method. Frame-back method is a dense optical flow analysis technique. The method approximates the window of image frames by a quadratic polynomial with the help of polynomial expansion transform. Then motion magnitude map is estimated by observing how the polynomial transforms under the state of motion. After applying optical flow analysis, we filter out the values lower than a predefined threshold. So the process removes the small motions, illumination variations, and small noises. You can see here different results with different thresholds. Then we combine the magnitude maps provided by applying the optical flow analysis on each frame to create a 3D matrix containing the magnitude of local motions across all the process frames. Then we calculate the probability map based on the number of flow occurrences for each frame. Additionally, at the next step, a histogram-based segmentation is applied to filter out the areas with low probability value and determining the hotspot and area of interest. To further analyze the probability map of gas flow, two regions are determined. Hotspot area, the area with highest flow intensity. The last section is experiments. In the first experiment, a thermal camera recorded a gas emission from different containers to be used for detection process. We conducted this experiment in Torngat Company in Quebec City. The camera was FLIR GF620, which is a cooled camera, and the gases was gasoline and alcohol, which were in the containers, and we used them to show the gas emissions, as you can see the result in the video in the slide. The second experiment was conducted with the gas with dataset that is actually available in the reference provided here. The camera they used was FLIR GF320 operating in the normal mode. The distance between the camera and the gas leak and the gas emission was varied between 4.6 meter to 15.6 meter. The target gas was methane, and the location was Methane Emissions Technology Evaluation Center at Colorado State University. You can see here the result of some samples showing how the algorithm behaved using this data, and you can see what was the results. The other experiment conducted in Tonga Company using a GI Magic probe and a cool camera FLIR GF309, which we use it as a handheld camera in this experiment. So we used the drone footage to first test the video stabilization technique that we used, and second to investigate how the algorithm behave using a visible footage instead of thermal image. Also, we use the results for testing and evaluating the gas leak detection, as you can see here, the stabilization method, and what was the result of the combination of stabilization method and the gas leak detection method, both presented in this study. So the results of this experiment showed that for small motions, the stabilization method provides reliable performance. But for bigger movement, as you can see, as you can saw in the footage, at the end of the footage, the stabilization demonstrates poor alignment, and those poor alignments caused false detection of flows in two areas of the thermal footage. Thank you for listening to my presentation.